Hey everyone, Akil from Oxford Academy here. This is part 2 of our related rate series, and today we're going to be focusing on the conical tank problem. So, let's go ahead and get started. Water fills a conical tank at 8 cubic feet per minute. If the tank has a base radius of 3 feet and a height of 12 feet, how fast will the water level change when it is 4 feet? So, let's go ahead and translate this problem. And to translate this problem, we're going to be using a diagram here. So I went ahead and drew out what it looks like a conical tank. Obviously, it's not to scale, but it will do the trick for now. So we know it has a base radius, which we're going to indicate with capital R, of 3 feet. We know it has a height, which I'm going to indicate with capital H, of 12 feet. And we also know that the water level is 4 feet. But what is the water level? Well, the water level is the level or the height that the top of the water is at. So, let's go ahead and draw that here. So if we go ahead and draw it, I'm going to go ahead and draw approximately right here. It's obviously not to scale again. So, this will do the trick. So this right here, this height, which I'm going to indicate with a lowercase h, this is the water level, and it is 4 feet. We're given that. So, let's go ahead and try using the information we know, which is dV/dt, 8 cubic feet per minute. Let's go ahead and try plugging that into a formula and seeing what we can do with it. So, we know the volume of a cone, which is slightly important here. The volume of a cone, that's 1/3 pi r squared h. And now we want to try implicit differentiating this, but we can't do that. Why can we not do that? Well, take a look here. We have volume, which changes with respect to time, height, which also changes with respect to time. But because volume and height are changing, the radius of the water has to change too. So we have multiple different changing variables, and we have to use the product rule for right now, because the thing is, we can't really use the product rule. Why? Because we don't know how fast the radius changes with respect to time. However, there's this fix to this. What we can do, we can try getting r in terms of h or h in terms of r. Let's put r in terms of h here. So, by doing that, let's go ahead and use proportions here. Why can we use proportions? Because take a look. We have a right angle here between radius and height, and we also have this angle right here. If we go ahead and draw the same angle over here, or if we go ahead and draw a triangle here, you notice we have a right angle and this shared angle. So we have similar triangles. So what we can do, we can go ahead and use a trigonometric ratio to try to find a similarity. So, let's go ahead and say that, this is tangent theta that we want to use. So, tangent theta, this is going to be equal to this unknown radius over this given h, which is equal to 1/4, which is going to be equal to 3/12. 3/12. So, let's go ahead and multiply h on both sides. So, r is going to be equal to 3/12 times h, which is equal to 1/4 h. Now notice, I didn't plug in 4 here necessarily, because then if we plugged in 4, we wouldn't be able to get a relationship between r and h. So I just went ahead and left h as is, because we want to find r in terms of h. So, let's go ahead and use this expression and put it into this volume formula. By doing so, we get that volume is going to be equal to 1/3 pi times the height divided by 4, because that's the same thing as 1/4 h, squared times height. H over 4, all that squared, that's going to be h squared over 16. Multiplying everything out, we get 1/3 times 1 over 16, which is 1/48. So, volume is going to be 1/48 times pi times h squared times h, but that's just h cubed. Aha! Now what we can do is we can go ahead and do some implicit differentiation, because we just have 2 changing variables now rather than 3. So, let's go ahead and put our ddt and do our implicit differentiation. The derivative of volume with respect to time, that's just dV/dt. And the derivative of 1/48 pi h cubed, so that's just going to be 1/48 times pi, because those are constants. And then the derivative of h cubed is 3h squared. But remember, implicit differentiation, we have to put a dH dt next to it because h is our variable. So now what we can do is we can just solve for dH dt because we're looking for how fast the water level will change. That's the rate of change of the water level, or dH dt. So let's go ahead and plug in our knowns. So when we plug in our knowns, we know that the height is 4 feet. So we get that this is equal to 1 over 48 times pi times 3 times 4 squared, which is 16, times dH dt. And we also know that the rate of change of volume with respect to time, that's 8. So let's go ahead and do some simplifications. 3 times 16 is 48, but we have a 48 in the denominator. So this and that cancel, and we just get that 8 equals pi times dH dt, and therefore dH dt is equal to 8 divided by pi feet per minute. Now, this right here is our exact answer. In terms of decimal answers, this would be approximately 2.5, 2.6. I'm sorry, I'm covering that a little. Approximately 2.5 or 2.6, somewhere around there. But yeah, this right here is our answer, and that concludes the conical tank question. This is Akil from Oxford Academy signing up. I hope to see you in future videos.